In this work, we revisit token pruning for vision transformers, and introduce a selective vision transformer for object detection and instance segmentation. Token pruning is a method to reduce the number of tokens in vision transformers. The redundancy of input images allows a removal of some unimportant regions such that the model can have faster inference speed and still maintain a good recognition accuracy. However, current methods struggle to extend to downstream tasks and are confined to classification. We therefore ask a question: can token-level pruning become compatible with dense prediction tasks? To achieve this goal, we re-evaluated the designs of token pruning within the context of dense predictions. This led us to a compact selective vision transformer that can first prune tokens on object detection and instance segmentation. The process begins with splitting an image into non-overlapping patches, and transforming them to tokens by a linear projection. Then, the tokens are passed through a gating network, and produce per-token masks indicating which tokens to use for the ViT block. These tokens are collected and reshaped to a new tensor, and are passed through a ViT block. Then, the processed tokens are scattered back to their original locations in the feature map. In this way, the pruned tokens are not discarded but kept unchanged in the feature map, while the used tokens can still update their values. This operation makes it possible to maintain a complete feature map, which is required for typical detection frameworks. Our experiments suggest that removing pruned tokens by padding zeros do not enhance performance, and preserving tokens has better performance for multiple models as seen in red columns. After pruned tokens are preserved in feature maps, we further reactivate previously disabled tokens according to new predictions from the gating network. The gating network is allowed to select previously unselected tokens and thus is able to reactivate tokens. Our ablation studies reveal that reactivating tokens can improve detection accuracy within a given computation budget because the model has a wider range of tokens to choose from. We also add a dynamic pruning ratio to adapt to images of different complexities. The intuition is that simpler images require fewer tokens and complex images require more tokens. Our experiments demonstrate that dynamic ratio can help allocate computation resources reasonably and improve the overall performance, especially when combined with reactivation. Finally, we simplify the design of gating networks. We verify that a simple two-layer MLP is sufficient to provide most of the performance of complex gating networks and is a simpler and lighter choice on dense tasks. Our experiments on COCO object detection and instance segmentation present that token pruning methods can accelerate ViT adapter backbones by 46%. With some loss of accuracy. Our selective vision transformer provides about 1 AP or more improvements over other token pruning methods and preserves most of the performance of a dense ViT model. Moreover, our approach also shows that the heat maps of token usage highly align with image semantics. You can find our code and models on our GitHub page.